Mashburn, and today I'm going to talk to you about resting membrane potential and action potentials. And this is part of the course that, part of this is found in Chapter 11. It's a little bit of the cart before the horse type of a thing. So if you're looking for this information, it can be found in Chapter 11. You've got to know how the nervous system works and how it innervates the muscles in order to understand how the muscles contract. So you got to go and kind of read ahead and then come back and do Chapter 9. Hopefully you have already watched the video about the nervous system, the neuron, and how the neuron is set up and the structures of the neuron. So I'm going to talk to you today about membrane potential and action potentials. And what I'm talking about today is basically the electricity, basically how the nervous system sends that impulse or that signal to the muscles. The signal we keep talking about, the way a nerve will make a muscle contract, is basically an electrical event, and we call it an action potential. And let me get my pen started. Forgot to do that. So basically, a neuron will conduct this electrical impulse, or this signal, that we call the action potential. And the way this happens is it's basically just a flow of positively charged ions, sodium and potassium, across the membrane. So sodium and potassium just basically flow across this membrane, and they cause a charge. It's a lot like a battery, and I'm going to kind of show you a picture of that and kind of explain how that's set up. In order for this to happen, you have to have channels. And remember, channels are basically proteins inside of a membrane that allow things to go through a membrane. So, for example, it's basically a hole punched in the membrane using a protein that allow ions to flow through it. Well, these particular channels are voltage gated. That means they open and close based on the voltage, just like a battery, like you're measuring the voltage of a battery. So as the voltage changes, these proteins will open and close. And when you look at a neuron, only the axon can do this. The action potential only travels down an axon, not down dendrite or the cell body. So let's kind of go back and review neuron anatomy. If your cell body, these are your dendrites. So information, say from the brain or wherever, is coming in. It's going to come into the dendrite, go through the cell body, and then you're going to want to generate a signal or an impulse to send down to the muscle. And so the action potential only goes from the cell body, impulse direction, down the axon to the axon terminals, and there'll be a muscle over here. So what we want to talk about is this actual action potential. How do we generate it, and how is it carried along the axon? So remember, there's not any action potentials up here, just in the axon. Alright, the way we do this, first is we have to basically set up our membrane potential, which basically we have to set up our battery. And that means you've got to have, think about a battery. If you look at a battery, there's a positive side and a negative side. We want to set that up inside of our cell. And the way we do that is we use ion channels, these membrane ion channels, and we have two kinds. We have what are called leakage, or non-gated, and gated. So a leakage channel is always open. So if you have, remember your membrane looks something like this. You have your little phospholipid bilayer, and there's going to be a protein embedded in that. Well, a leakage channel, it just has a pore basically inside of it that allows things to travel through that channel. A gated channel means it opens and closes, like a gate. It will open, it will close. And there's two types of gated channels. Ligand gated, which means something has to bind to it. Some protein, something has to bind in order for it to open. Voltage gated means it only opens or closes depending on the voltage, or the membrane potential. With the actual voltage or potential, you were able to measure the voltage of a cell. When it reached a certain voltage, this gate would open. And you actually can do this. Let me go ahead and tell you that you can measure the voltage of a cell. In graduate school, I did this. You would take a cell, use a microscope, and you would take a little bitty pipette, a little bitty thin piece of glass, basically, insert it into the cell, and it would be attached to a voltage meter. And you could actually measure the voltage, just like a battery charger. When you hook up your battery charger to your battery, and it tells you what the voltage of the battery is and how much you need to charge to make it go, you could actually measure what the voltage was inside of the cell. So that's what we're looking for. We're looking to see how we generate that voltage. I've got a picture to show you these gated channels. These are the ligand gated, and so basically on a ligand gated channel, there'll be some kind of a site, a binding site, and then something, in this case a neurotransmitter, will bind to that binding site. And so when it binds, this opens up and allows sodium and potassium to flow through. It opens it up. So it's ligand gated. Voltage gated means you have a channel and it's closed right now, and this is your battery. You've got your pluses here, your minuses here. As the voltage changes, you can see its reverse polarity. It's negative down and positive here. As that voltage has changed, it's opened up the channel, and now the sodium can flow through. So that's the difference between a ligand gated and a voltage gated. Ligand gated means something physically has to bind to it to make it open, and voltage gated means you just have to change the charge on the membrane for the protein to open up and allow the ions to flow. Alright, so before we can generate an action potential, we have to generate a resting membrane potential. I don't know why that's so tight right there. There's space. We have a resting membrane potential. So we're going to set up our battery. Alright, so this is something I told you. You could take a little voltmeter and you can actually measure this. And if you measure the voltage of a cell, it's about minus 70 millivolts. Okay, and what that's telling me, because it says minus 70, is the inside of the cell is negative relative to the outside. So it's minus 70. So the inside is more negative than the outside. And the way this occurs is there's a difference in the ionic makeup, the amount of sodium and potassium, basically, inside the cell and outside the cell. And this difference creates this battery. So you've got to remember, you've got to go back to Unit 1, basically, and remember your cell, your intracellular fluid, and your extracellular fluid, and remember the makeup, the ionic makeup of both those compartments. We're talking about the neuron. Generally, the level of sodium is higher outside the cell than it is inside the cell. Potassium levels are lower outside the cell. They're higher inside the cell. And these are both positively charged. And then if you've got a positive, you've got to have a negative, right? Well, on the outside, the negative ion is basically chloride, and on the inside, proteins actually have a negative charge. And so in this scenario, if your membrane is permeable to both sodium and potassium, sodium's going to move in, because remember, sodium goes down its membrane. It's going to diffuse across the membrane, going down its concentration gradient, its passive transport. Potassium's going to flow out. So finally, they're equally, you have a neutral charge on either side. That's what you'd expect to happen. Well, that's not what happens, because you want to have more potassium inside and more sodium outside. If you just let this membrane reach equilibrium, there would be no charge. So in order to have charge, you have to have what's called a sodium-potassium pump, and you have to know one more little secret that you don't know that I know. When you talk about these leak channels, for every one sodium leak channel, you have 75 potassium leak channels. So let's pretend this is the sodium channel, and this one is, these three are all potassium. Okay? So, by diffusion, passive transport, sodium's going to flow in, right? So it's going to take its positive with it. Potassium, because there's more leak channels, potassium's going to be flowing out really fast, taking its positives outside. Well, because more positives are leaving than positives are coming in, then the net makes it negative on the inside and positive on the outside. And so you set this up. So basically, more potassium leaves the cell through these leak channels than sodium enters. So more pluses leave than pluses enter, and that gives you a net negative inside the membrane. Now, again, all things being equal, if nothing else happened, eventually enough potassium would leave and sodium would come in that it would reach equilibrium, and you wouldn't have your battery. So to prevent that, you use a pump. This is the sodium-potassium pump. And if it's a pump, that means it uses ATP, which means it's active transport. And so what you're doing is you're actively pumping sodium against its gradient, and you're pumping potassium against its gradient. You're pumping potassium back in. So as you keep pumping potassium in, that keeps replenishing the potassium inside the cell so that it can continue to leak out and generate this battery. So that's how you get your resting membrane potential. So you have to set that up at the very beginning. You can't get action potential without having your battery set up ready to go. Alright, so just kind of one more schematic to kind of get it in your mind. Sodium concentration is higher outside the cell. Potassium is higher inside the cell. You have these leak channels which allow potassium to flow out. You have more potassium flowing out than you have sodium flowing in, and you have the sodium-potassium ATPase, or sodium-potassium pump, that will then pump sodium in, or sodium out, and potassium in. So that's the way you set up your resting membrane potential, or get your battery ready. Alright, so when these membrane potentials change, when these concentrations start to flow, and these ions start to flow in a particular pattern, they start to change the voltage of the membrane, and that basically is electrical signal. And we call that the action potential. Okay? So when you get this change in membrane potential, sodium and potassium are moving across the membrane, causing this voltage to change, we give that a special name called an action potential. And we've got several stages of an action potential that are kind of standard, and you need to learn them. The big picture, and I'm going to go under each step and explain what's going on in each part of the action potential. But when you look at an action potential, it can always be broken down into 4 steps. Okay? You have what's called the resting state, and this is just the beginning. You've got your resting membrane potential, your battery's charged, ready to go. Okay? Your second step is called depolarization. It's becoming depolarized. It's actually the membrane potential is becoming more positive. Okay. Then you have a repolarization, where the membrane is becoming more negative. Then you have hyperpolarization, where basically it goes below the original level. It's hyperpolarized. It kind of overshoots the original threshold before it reaches back and goes back to where it was. So what we've got to talk about now is what's causing this depolarization, what's causing this repolarization, and what's causing hyperpolarization. Well, I can tell you it's just a movement of ions, and it's a movement of sodium and potassium. Those are the 2 ions that are going to be moving. And I'm going to give you a little hint. Sodium's moving over here, and potassium's moving over here. So let's talk about how, where, and why. Alright, so in the resting state, remember, we've only got your leakage channel. That's the only thing that's open. Sodium and potassium are just kind of moving back and forth, and that sodium-potassium ATPase, or sodium-potassium pump, is generating that resting membrane potential, keeping your battery ready to go. So that's what's going on. Sodium's coming in, potassium's going out, and the sodium-potassium ATPase is keeping that battery charged. Now, you have sodium channels. You have some voltage-gated sodium channels. I always talked about so far the leakage channels. These are just the leakage ones, the ones that are always open. You've got an extra set of channels inside the membrane, the voltage-sensitive ones, and they're going to open and close based on changes in voltage. So they're going to, we call them activation gates. Basically that means they open. Inactivation gates means they close, basically. So these activation gates are going to be closed, and they're going to open during depolarization. And your inactivation gates, they're going to be open at rest, and then they're going to close. They're going to block the channel once it's open. So basically, you just got a little gate that's going to open and close based on the change of charge. Potassium channels, they only have one gate. It's always closed at rest, and it only opens with depolarization. That's not the most, you don't get too tied up in those kind of details. I'm just kind of showing you what's going on there. Alright, so during depolarization, you're starting to get a change in current. Alright, this voltage is starting to change. And it's going to cause those voltage-gated sodium channels to open. And as sodium, here's your cell, your sodium's high out here, sodium's low here. You're going to have these membrane proteins, these voltage-gated channels, and as they open, it allows sodium to flow in. Okay? Remember, sodium's positive, and you've got these voltage-gated sodium channels, and lots of sodium is all of a sudden starting to flow in. Well, it's bringing those positives in with it. So that's going to start making the membrane more positive on the inside. So let's look at our action potential again. So as sodium's flowing in, the membrane potential is becoming more positive because more positives are flowing into the cell. It's depolarizing. Alright, now once you depolarize the cell, it's going to reach a certain threshold. And then those sodium channels, the voltage is going to get to a certain point. When the voltage becomes around positive 30, the sodium channels close. Those gates close back down. And no more sodium can come in. So sodium no longer is coming into the cell. Alright? At that same time, you have some voltage-gated potassium channels opening. So now, potassium can leave the cell. So remember, you got the cell, your sodium channels are closing, so they're shutting off, so no more sodium can come in. And at the same time, another set of channels opens and allows potassium to leave. Well, no more sodium's coming in, so no more positive charges are coming in. You have a bunch of potassium leaving through some voltage-gated potassium channels, so your positives are leaving again. As your positives are leaving, that starts to bring that membrane potential negative on the inside again. It starts to lower the membrane potential back to negative. So let's go back to our picture. Go back to our action potential picture somewhere. So here, your sodium channels have closed. No more sodium's coming in, so it's not going to get any more positive. Your potassium channels are opening, so your potassium is leaving the cell. So as those positives are leaving the cell, your membrane potential starts to go back down again, starts to go back down or repolarize. Now, you've got this little thing called hyperpolarization. And what happens there is for just a short brief time, some of the potassium channels stay open just a little bit too long. They're open just a little bit too long, allows a little extra potassium to leave. Because you've got that little extra potassium leaving, it kind of goes too low. It or it overshoots the original threshold level. After these gates then close, the sodium potassium ATPase or sodium potassium pump will continue to work, pumping potassium back in and reestablishing the threshold membrane potential. Alright, now this is real important. This hyperpolarization is really important because it allows the membrane potential to only travel down the axon in one direction. So hopefully I'll be able to show you that in just a second. If you have not watched those A&P flicks, okay, that I have assigned, make sure you do that. That's a really great way to see this because you can actually see it in 3D. You see the animations. You can see the ions flowing. I wish I had that when I was in school. All I had was a chalkboard. So if you have not watched the A&P flicks, go back and watch them. It will make this so much clearer if you can actually see all that happening in 3D. Okay, so we're going to put all this together. Here's your action potential. Depolarization, repolarization, hyperpolarization. During you have your threshold, you have your membrane potential, it's ready to go. You have the stimulus, voltage-gated sodium channels open, sodium rushes into the cell. So sodium channels close, potassium channels are open, potassium leaves the cell. stay up a little bit too long, overshoots the membrane potential, and then rises back to threshold. And that's basically the steps of an action potential. Now, remember, none of this will be possible without the sodium-potassium pump. You have to have that sodium-potassium pump so at the end it can basically redistribute your ions back to resting conditions and recharge your battery and have it set for the next go-around. Remember I told you that hyperpolarization was important because it only allows an action potential to go in one direction? Basically what happens is action potential is just these charges just kind of, it's called pulsatory conduction. They basically just move down the axon. So you have this flipping of charges where there's going to be positive, negative, positive, negative. It's just going to move all the way down the membrane in one direction. Because this is hyperpolarized, so if you can imagine, here's an action potential here. And so when you want to generate the next one, in order for sodium to come in, you've got to be able to stimulate it and open those sodium channels so that sodium can flow in and depolarize the cell. Well, because this area of the membrane is hyperpolarized, you can't get those sodium channels to turn on. It won't go the other way. So you can't generate an action potential and make it go that way. The only part of the membrane that's ready to go, that the battery's ready and primed for sodium channels to open and the action potential to go the way it's supposed to, is on this side. So that hyperpolarization basically ensures that your action potential only travels in one direction. Alright, now I've used the word threshold a couple of times, and I want to make sure you understand what that means. Threshold is basically the voltage that is required in order to get a stimulus. In order to generate an action potential, you've got to give it just enough stimulus in order for anything to happen, for those sodium channels to open. And again, when I was in graduate school, you could take a cell, put a little voltage meter in there, and then give something else, a stimulator, lost the word, a stimulator, and you could figure out which voltage, which stimulation would cause an action potential to be generated. So if you had, just think about like a taser. So let's just say I zapped it, nothing happened. Let's say I zapped it with 3 millivolts, nothing happened. Well, that's sub-threshold, okay? If I zapped it with 4 millivolts, okay, and I was able to use my voltmeter and see that an action potential was generated, I would know the threshold was 4 millivolts. That means it takes at least 4 millivolts for that cell to generate a stimulus. Alright? Now, if I then zapped it with 5 millivolts, I would still get an action potential because it's above threshold. But the action potential is not going to be any bigger or any faster or any greater. It's just going to be another action potential. So once you reach threshold, you just get an action potential. It doesn't make it any bigger or anything like that. Basically, it's all or none. You either get one or you don't. And this becomes real important when we talk about muscle contraction, especially how much, I like to use the word brain power, how much electrical impulse you got to send from the central nervous system out to the muscles in order to get them to contract. If you don't send enough, nothing happens. You're sub-threshold. If you send enough brain power or signals out from the central nervous system to the muscles, they'll contract. That's real simplistic, but it kind of gets the point across of what we're trying to show you at this level. We'll talk to you more about that in Unit 4. Okay, and this slide, this is a really nice overview slide. It's got everything on there to kind of tie in together for you. You've got your action potential on here. You've got what's going on. So remember, you're going to have your resting state where you generate your membrane potential. It's showing you that you have, there are link channels where sodium and potassium can be moving. Sodium's moving in, potassium's going to be moving out, but none of your gated channels are open. Nothing's going on there. No gated channels are open. You stimulate it here. That allows sodium channels to open. Okay? As sodium channels get open, this becomes more positive on the inside. As it becomes more positive, more and more sodium channels open, allowing it to become even more positive. When it reaches about positive 30, the sodium channels will then shut down. The potassium channels will then open, potassium will leave the cell, and as the potassium leaves the cell, it will overshoot for a little bit longer, so it continues to go out, then these will shut down, and then your sodium-potassium pump will reestablish the membrane. I know that's a lot of information, and it's probably one of the most difficult concepts in physiology. It's one of the first times you're going to see some real physiology that's kind of complex. So watch this video over. Make sure you watch it a few times. Watch those A&P flicks. And then I tell my students, take a piece of paper. You need to be able to think about it in your head. Draw yourself. Set up your battery. Figure out which ions. Where is sodium out here? Potassium's here. Set up your battery. Which way is sodium going? Which way is potassium going? What's your pump doing? And then just kind of think about it stepwise until you can kind of do it from heart on a piece of paper. You can draw out action potential and all these steps going on. It seems impossible, but trust me, you can do it. Now the next thing you're going to learn about is going to be the neuromuscular junction, and what this is going to be where the neuron and the muscle come together, and how you're able to get that signal from the neuron to the muscle and actually have a muscle contract. Alright, I'll see you later. Good luck. If you have any questions, email me, call me, and good luck.